Thank you very much, Yuto. It's a great pleasure to be here. I was reflecting as I was walking around Vienna that so many wonderful discussions and projects really had their birth in Vienna over the past decades with the likes of Jens and Yuto. It's great to see you all again. And in particular here at ESI, I've had the good pleasure to be here a number of times, and it's always been incredibly inspiring as a place. And so this time has been no exception, and I'm very pleased and honored that I've been given the last talk slot for this workshop. And furthermore, that there are so many people in the audience. I had sort of anticipated that there would in fact only be Yuto and Dom here, and thought maybe I shouldn't need to prepare a talk, and instead we could just chat. Okay, so I did prepare a talk, and now I'm maybe relieved that I took the effort to do so. Okay, so the title of this talk is Quantum Simulation of CFT. The first thing I really want to address is what on earth has that got to do with tensor network states. As the talk progresses, you'll see that it has quite a lot to do with tensor network states. The work in this talk that I want to share with you is joint work with Alex Stockmeister, postdoc at Hanover. He's really done extraordinary things in the study of discrete approximations to quantum field theory in the last years. I think if you just search for his name on the archive and pick any paper post-2019, then you'll get to see some really interesting stuff. And so in a way, I feel like my role here today is to advertise the stuff that he's been doing, but also to relate it, I think, to the context of quantum simulation and tensor network states, which is the topic of this conference. So I'll start with the question of why on earth talk about such things. I'm going to talk about what is simulation. I'm not really going to talk about QFTs, CFTs. So really, I guess I'll be talking about implicitly quantum field theory. I mean, CFTs were the motivation for this. And in fact, I'm not even going to talk about like all the results that we have in this direction. In fact, I'm going to just specifically focus on one key ingredient that I feel is absolutely central in the study of simulating any kind of quantum field theory. Share that with you through this talk. So yeah, the first thing to explain to you is why this topic. And I guess my quick and dirty answer is, if you care deeply about simulations, then the reason why you would study simulations of CFTs or QFTs is you have to answer hard questions. And answering hard questions is always fruitful, especially in the quantum simulation or any simulation domain. And the hard questions will invariably force us to wanting a mathematically rigorous formulation of quantum field theory, which in its entire generality, in a way that satisfies physicists, doesn't yet exist. So it's hopeless, right? You know, from the outset, the objective of this talk, how do we simulate CFTs, QFTs, in a way that would satisfy a physicist in a mathematically rigorous way, is not yet possible. This talk is not yet possible. I can't give this talk. But what I want to do is I want to explain to a largely physicist-based audience, mathematicians, what I think is the hard aspects of answering this question. And in a way, I was surprised when I finally discovered what was really hard about simulating quantum field theories. I was pretty surprised what was the hard element. It's like, there's no making this nice. It's hard. We're never going to be able to just sort of have some functorial way of solving all quantum field theories that are relevant to physicists with all nonlinear interactions, blah, blah, blah. It's not going to happen. But it's very interesting where the difficulty lies for a physicist, especially a tensor network-based audience, and how we can concentrate our efforts on making progress on this difficult part. So that's what I'm hoping to isolate in this talk. That's the goal for the talk, to specify what I mean by hard question and show you where the hardness is. Why is it difficult to do these kinds of things? Now, before moving on to the quantum fields, I want to talk to you about classical systems, classical fields, and why this isn't even a topic, right? You know, why is it that classically things just aren't? In the classical situation, people who talk about, you know, the existence. Does a classical field even exist, right? You know, do we know how to do it? Like, do we know how to simulate classical fields? Well, of course we do, right? We've been doing it for decades, if not centuries now. You know, if we take, for example, the electrostatic field, I just choose that as a particular example, right? Here's the electric field. There's Maxwell's equations. Okay, it's an electrostatic situation. We have some charge distribution that we've obtained through, I don't know, measurement of some material, and then you want to find out what's the electric field. Well, introduce the potential, and then you reduce the problem to solving Poisson's equation. And then, this is all continuous, right? Nothing discrete here. But then to put it on a computer, and there comes this moment, like in physics, where you have to transfer from mathematical existence and so on, and you have to put it on a computer because you have real data, and you want to get real answers, and you want to be able to sort of write them down. And you could do it by pencil and paper, but we've reached the point where charge densities are so sufficiently complex that we cannot write them down as a list of numbers on a piece of paper. So we have to put them on a computer. And then to actually solve something like Poisson's equation on a computer forces you to discretize, right? So this is, I mean, you might do it in Fourier space, you might do it with wavelets or something, but in the end you're taking a continuous infinity of data and replacing it with a finite list of data. So the way you would then solve this sort of thing is you discretize, and I don't know, you put it on a grid, right? You might use finite elements, you might use finite difference scheme, but you will have some way of discretizing your continuous data, the electrostatic potential, and then you put it on some discrete grid that's sufficient to resolve the data that you have, namely the charge distribution, and then you have to solve Poisson's equation. Okay, you know, probably most people would use fast multipole method, I guess, today, but if you were, you know, back 30 years, you could use the finite difference method to solve this continuous differential equation, and so you replace phi by a list of numbers that just give you the field, the classical potential at the grid points, and then you you solve these kinds of x, y, these kind of finite difference schemes. You end up with linear equations in a finite list of variables. And now comes the crucial ingredient, one that I think we just take for granted, and one that I'm going to sort of focus on for the rest of this talk in the quantum setting. If we have a discrete solution, you know, we just end up with some list of numbers after solving these linear equations that come from finite difference, finite element, blah, blah, blah. You know, we have a list of numbers. After having these list of numbers, we ask the question, how good was that? How close was that to the correct solution, the continuous solution? And we can answer that question pretty easily in the classical case. We have a list of, this is 1D slice, right, through the potential. And then we ask the question, how close was this to the perfect continuum solution? And it's easy. We know how to answer this question because we have a thing called interpolation. We can interpolate the data, this discrete data. We can draw maybe straight lines or splines or sine x over x or whatever interpolation scheme you happen to prefer. We construct a function that now lives in the same space as where the ideal Platonic function lives. And now we're free to deploy whatever norm we like to check that the discrete approximation is somehow close to the continuous approximation. So I want to emphasize that, you know, the ideal solution can be compared with the numerical solution because we have this thing called interpolation that allows us to embed discrete functions into the continuum where we can then meaningfully and honestly compare with the ideal Platonic solution to the actual differential equation like this. This is a key ingredient. I'll come back to that as the talk progresses. The idea that we need to be able to compare things at different scales and indeed compare the discretium to the continuum. And I think that's the key theme that I want to carry for the rest of this talk, is how to compare the discretium, I don't even know if that's a word, with the continuum for, let's say, quantum many-body systems. All right, that's the big question. How do we do it? I'm going to explain how to do it, and I'm going to do so by channeling Wilson. So Kenneth Wilson really answered this question, in my opinion. Most physicists today aren't bothered by these things because they know about Wilson. And Wilson taught us how to understand discrete approximations to quantum field theory. And my goal is really to channel Wilson and to give you a Hamiltonian picture of Wilson's explanation. So the key point here is that Wilson, in a way, to the satisfaction of many physicists, explained how to understand quantum field theory. And he did so with a path integral language, right? So if you go read Wilson's papers, all of his, apart from the numerical renormalization group paper, I'm really referring to Wilson's RG, not Wilson's numerical RG. So if you look at Wilson's original paper, then you will see that it's written largely with a language of path integrals, which causes allergies to some people, but I don't think that's the reason why I would prefer a different formulation. It's that it's not very compatible with tensor network methods. So what I want to do is, for the rest of this talk, is to explain how to give a Hamiltonian formulation of Wilson's formulation of quantum field theories, which is compatible with tensor networks. So that's why, quantum simulation up here, I'll explain what quantum simulation is there. That gives us a free pass here in a second. So there's a Hamiltonian version of Wilson, and that's the one I want to introduce. It has a name now. It's called operator algebraic renormalization. It was sort of slowly came into being over a sequence of papers. I will at some point.
Otherwise,
yep.
Tensor Networks could equally well deal with the problem. It's really the quantum simulation that requires the Hamiltonian.
Yes, Tensor Network could equally well deal with the path integral. That's absolutely true. And I'm not saying that Tensor Networks cannot use the path integral formulation, but a Hamiltonian formulation would just be a bit easier, right? Force, I guess, if you want to deploy DMIG from an off-the-shelf solver to some problem that I'll explain.
In many cases, finding fixed point of transfer matrices is easier than algorithmically. Implementation-wise,
this is true.
Easier than
Yeah. You make a good point. Once you see the answer, maybe that'll explain why I think this is a worthy thing to try. So the operator algebraic renormalization group, it was introduced over a sequence of papers. I guess, morally speaking, it started out with a paper of Zini and Wang, where they looked at continuum limits of certain lattice systems. So I also had a paper on continuum limits of quantum lattice systems, I think it was 19 or so, and then lots and lots of papers by Alex. Developed this framework. So there is this thing now, there is a Hamiltonian version of Wilson's formulation of quantum field theory. It's called operator algebraic renormalization. Okay, I've put G to group, that's a matter of taste. And the goal of today is to just explain to you the definitions of this operator algebraic renormalization, explain why should you care, and show how it isolates the hardness of the problem of showing the continuum limit of a lattice system, comparing a discrete lattice system with a continuum. And so, yes?
Sorry, maybe that's the wrong time to ask this question, but there's also the work by John Preston and others who looked at going from the continuum to the discrete setting by Hamiltonian formulation to then make predictions working at different scales.
Indeed.
So how does this relate to?
I will do that in the next Blackboard.
Next slide.
Yeah, the next slide, so to speak.
Very good.
Indeed, good. Yeah, that's a very important observation. just before doing that, I'll say what's the difference between quantum simulation and tensor network simulation? I would like to argue that the difference is that you get unitaries for free. Like you can do polynomial evolutions or polynomial depth quantum circuits for free when you do quantum simulations, but for tensor networks, you don't get that for free, right? That hurts. You can generate a massive amount of entanglement with a polynomial depth quantum circuit. So quantum simulation is, generally speaking, sort of easier to reason about than just straight up tensor network methods where you don't get time evolution for free. So that's a key thing. Okay, then Jens already foreshadowed the question. What's this got to do with the work of Preschool? And there's been a tremendous number of very important works in this space, the space of simulating quantum field theories. Like, you know, I would have to do a great injustice to the amazing works of the lattice QFT community who have been looking at precisely this problem for like decades and have come up with incredible results. So, yeah, well, here's a quick summary of simulating QFT. We've had decades and decades of progress. Well, I mean, I think, you know, perturbative QFT's got to count, right? That's arguably the first way we had to simulate interacting quantum field theories. Then came, you know, Wilson again came along and explained to us how we should simulate using a computer the dynamics of a gauge theory, and that led to the now extraordinary field of lattice QFT. And then after that came lots and lots of work in the meantime with lattice QFT. This has really culminated in some extraordinary results. You might have seen this plot with the masses of these hadrons, right? You put in two bits of data and the mass of the K and the mass of the, I don't remember. And then you solve the lattice QFT and you predict the masses of the other hadrons. It's kind of an amazing result, triumph of lattice QFT. And it matches the experimental data up to error bars. That's a massive triumph for lattice QFT. After that, of course, we've had more recently, we had Tensor Network, Murray Carman. I guess the representative of this line of work in the audience. I'm not sure if anyone else is in the audience who's worked hard on that. Oh yeah, there are more in Matthew. Several of you have worked on tensor network simulations of QFT. They work, right? And they work surprisingly well in one dimension. Higher dimensions is non-trivial. It's a work in progress. More recently, I guess, comes quantum simulations, where of course you get time evolution for free. And then they're the results of Preschool from quite a few years ago now, simulating the 5-4 theory. Gave us the first indication that quantum computers might be a useful thing for the simulation of quantum field theories. In particular, they evade the sign problem, right, that afflicts the lattice QFT calculations. And I guess that's a very quick summary of the strands of thought that have been applied to the study of quantum field theories with computers. I would argue that all of these approaches care very much about how does the actual computed result compare with the correct result of the theory? And various Hail Marys are invoked at various points to make that comparison, right? And so for the Preschool, the result and the papers emerging in that direction, the Hail Mary that's invoked is that you don't really ever make that comparison. You just say, we'll study a lattice model, and we know that it's in some universality class, therefore it is a legitimate simulation of some quantum field theory, but we're not going to solve the quantum field theory and compare it with the exact result. That, I hope, is a little bit dissatisfying, because otherwise there's no motivation for this talk. So that it's kind of that thing here that I would love if we could do better, right? Wouldn't it be great if we took our favorite quantum field theory, stuck it on a quantum computer or a classical computer, computed a result on a lattice, and then we said, we hereby promise that the answer that we get is within epsilon of the correct answer.
So the point has been, these things have no guarantees, right?
There's no guarantees.
Because,
I mean,
who's guys in the know for the best, and you want to have, like, for all scales, a guarantee of your prediction.
Absolutely, yeah. I mean, I think the classical situation has encouraged us to want that. You know, we have a massive number of techniques in numerical analysis that will give precisely these guarantees. The lattice spacing is small enough that you get an answer which is close to the exact result. You know, why not? Why not ask for guarantees? Well, it's hard, right? Because you need to have solved and proved the existence of quantum field theories as mathematical objects, which we don't have here in general. We have it for some number of cases. And we, you know, these cases will emerge as this talk progresses, right? It'll be clear that that we're not going to offer anything new here. So existence of QFT is hard. We can't compare it with something that we don't even know if it exists. So, right. Good. So then what we're going to do is argue what it is that we need to have to be able to make that comparison. And then we'll be like, okay, we know where the job is, where the hard work is to be done. And this is usually in a mathematical context. This is well understood. The existence of QFT has been approached by a large number of attacks, right? You know, algebraic QFT, constructive QFT. We also have functorial approaches. The existence of QFT as a mathematically well-defined object has been studied for decades as well, and there is a massive amount of progress. But I think that those results are hard for the physicists to interpret. So what I want to do is give a physicist-friendly explanation of, like, what's the hard bit, right? Why is it so hard? And that's what the rest of it, that's what operator algebraic algae has emerged to do. And by physicist-friendly, I mean to the physicist who likes Hamiltonians, as opposed to the physicist who likes path integrals. The physicist who likes path integrals, well, you know, you're probably already satisfied. You probably already know why it's hard. Okay, so I'm going to now dive in to explaining the Wilsonian formulation of quantum field theory, and then we'll see by parsing this explanation or this definition, if you like, we'll come down to some equations, and those equations we'll be able to solve. The core goal of today's talk is to explain something that Wilson calls his triangle of RG, which I foreshadowed over here on this board. So hopefully, you know, if at the end of this talk you understand what that means, then like I'll be pretty happy. Right? Okay, so what's Wilsonian's formulation of quantum field theory? What you've got to do is you've got to adjust a regulated theory by increasing cutoffs, sort of give you a parameterization of the regulated theory, while preserving, and this is crucial, low energy predictions, or long wavelength. And that's what Wilson taught us to do, increasing cutoffs while preserving low energy predictions. Wilson says that's how you've got to understand the construction of quantum field theory to a physicist. Nowadays, if you ask someone like Dan Harlow, he would say a quantum field theory is a lattice system. And that's the way to unpack that statement is actually via this formulation here. So what I want to do is explain these words, right? I want to give definitions for these things so that you can then meaningfully go away and apply DMRG to study it. Okay, let's start with a couple of words, right? Regulated theory. What does that mean? Well, we're in a tensor network audience here. Regulated theory can mean many things to many people, but to us it means lattice. It means a spin system, right? Many body spin system. Right? It's a And okay, done the first piece of data, explain what we mean by that. Cutoffs, what are cutoffs? Well, we've got a physical length scale here. Cutoff is the lattice spacing, right? We'll call that cutoff the lattice spacing A.
Sorry,
yep.
I don't want to be annoying, sorry, but I mean, like, all of this, of course, applies to quantum simulation, as you say, but equally well to tensor network settings. And I mean, we've ourselves like worked on CMBS and so on in the past. That kind of does the different type of cutoff in a way, like where the continuum limit is kind of built in.
Mm-hmm.
But when there was like others and also you like noticed that, oh yeah, well, it's great to have, but it's also good to stay in the discrete setting and then make predictions for all scales. So like all you say would equally well apply to the tensor network reading of that.
Absolutely, yeah.
Okay.
This is a particular instance of what we mean by cutoff spacing.
Okay.
But in the CMPS case, it's more like bond dimension is the cutoff.
Exactly.
Right.
An effective
Cutoff.
Yeah.
So every mathematically well-defined theory is probably has a cutoff and is regular. It's probably a matrix. Let's be honest, right? It's probably not even an infinite dimensional matrix. It's probably just a finite dimensional matrix. At the end, the equations that you'll be solving.
It's kind of more subtly hidden with the CMPS approach. That, like,
It's-
in a bond dimension, you have to introduce a cutoff yourself.
Yes.
Like somehow the having of a cutoff is integral to having a QFT.
Yes.
If you don't have a cutoff, you probably don't have a QFT.
And that's what we're going to get to right here. I mean, this is how Wilson explains it, right? Wilson says, don't start with what you don't know, start with what you know. So you start with regulated theories, which are well-defined as like just Hamiltonians on the lattice.
So is it essential that the helpless state of a site is also finite, that it's really spins?
No, it turns out it's not. No, it doesn't have to be spins. I mean, actually, the examples that I'll show actually include bosons. Like, it's going to be the usual candidates, like free theories.
I mean, so there's no cutoff needed there.
There's no local Hilbert space cutoff required, but I'm going to certainly put one in for the rest of this talk. Otherwise, we have to worry about horrible subtleties. And okay, so that's what we mean by regulated theory with a cutoff. It's labeled by a cutoff. I don't know how you do it, but I'm going to do it with lattice spacing. And then low energy predictions or long wavelengths. Well, what is this? Datum. What on earth does that mean? So for this talk, that means correlation functions. Can I reach just? Good. All right, correlation functions. This is what we mean, roughly speaking, by low energy predictions with a finite number of points. At certain physical locations. The physical means that if you scale the lattice, you make your lattice spacing smaller, then you have to talk about correlation functions of insertions that are further apart on the lattice, right? So that's what that's how you unpack, or you can unpack the Wilsonian formulation of QFT. And when you do so, you're faced with working out when things have a nice limit, right? And I'm going to talk about good limits, bad limits, nice limits, bad limits in the next half an hour, right? So something with a nice limit, which I won't even define because the rest of the talk will be aimed at defining that word. Intuitively, though, a nice limit should be clear, right? As you make the lattice finer and finer and finer, the correlation should sort of be non-trivial and converge to something, right? But what does that mean on the lattice? That means that the correlation length has to diverge. So this is where things get interesting, right? So correlation length psi, that has to go to infinity as a tends to 0 in order for there to be a non-trivial correlation function at all.
So what type of correlation functions do you have in mind?
I have in mind two-point static correlation functions, for example.
No dynamics, no finite temperature.
At the moment, not even that, yeah. We have to introduce our, the key ingredient I didn't specify, and I sort of left it implicit. When we have a regulated theory, there's a corresponding Hamiltonian on the Hilbert space of this system, and that Hamiltonian, and this is super important, depends on the cutoff, right? The Hamiltonian is cutoff dependent. So if you choose a finite lattice spacing, it better be that your Hamiltonian, or it doesn't have to be. In most cases, the Hamiltonian has to depend on the cutoff. Otherwise, you can't engineer it to have a correlation length that diverges as the lattice spacing goes to 0. Now, hopefully, this will start to look reminiscent of something that you're familiar with from condensed matter physics. And this is, you'll often hear this slogan, right? What sort of lattice systems have correlation lengths that diverge as you send some parameter to some special value? Right? They're called quantum phase transitions. So lattice systems exhibiting quantum phase transitions, you will sometimes hear physicists call them QFTs. I mean, I don't think I dare say that they are, but yeah, Matthias.
Just one question to be clear. So, the physical correlation length that should diverge, or the one in
the one in the lattice must diverge? Excellent question. Does the physical correlation length diverge, or does the lattice correlation length diverge? The physical one can be finite. It can even be exponentially decaying, but that would still imply that on the lattice that correlation function diverges. So you will hear that people say, oh, yeah, quantum phase transitions are QFTs, right? You may hear physicists dismissively say this. And that's the physics behind that statement.
In general, I mean, quantum phase transition and the QFT may go to the same fixed point, but they're not the same.
They're not the same, you're absolutely right, yeah. To talk about them being the same, we need to compare.
With some special phase transitions which happen to go close to some free theory or something.
We could spend hours perhaps talking about this point. I don't want to use that as a motivation point for a bunch of definitions, but I mean, you're right to pick on that, and as a card-carrying physicist, you probably could say a lot more than I can about this topic. Okay, what I want to do then for the rest of the talk and to get to that picture over there is to sort of specify something a bit more concrete so that you can now sort of relate to something rather than just physicists alone. So, all right, we're going to talk about lattice systems. Let's talk about 1D lattice systems. Everything I can say can be generalized to higher dimensions, so it's not really required that it's 1D. And I'm going to draw my lattice systems like this. I like the degrees of freedom to live on the cells rather than the sites. For reasons that will probably become clear pretty quickly, it's kind of nice to have your degrees of freedom living in the lattice unit, cells rather than the site. That means the total Hilbert space is C to the D tensor however many sites you have. How many sites do I have? There's two kinds of n in this talk, so I don't want to use them up already. Little n is the number of lattice sites that we have. And I see this Hilbert space here by little n. So it's a finite system. Like, I'm not even going to talk about an infinite lattice system. I'm talking about finite. It's a lattice lit. And we have some length scales here. Is A, the lattice length, however many spins we have, times by however many the lattice spacing, had beta equals some physical length L. That's also a number that we can send to infinity. There's various things you can send to infinity at various points in this discussion. We're looking at the continuum limit, but not necessarily the infrared limit where L goes to infinity. I think, for me, the most fascinating thing is, like, how do we compare something discrete with something continuous? So we'll be keeping L finite probably for most of this talk. Okay, and then we need also attached to every such lattice is a Hamiltonian, which I'll call some notation for it. HA, it's just some local Hamiltonian. J plus 1, and it depends crucially on that lattice space. And that's important for tuning yourself towards a quantum phase transition or to a place where the correlations diverge. If you don't do that, if you just choose the same Hamiltonian, you'll end up with a continuum limit. It's just boring. I've already foreshadowed the answer. Okay, and so associated to every such Hamiltonian is a ground state. And so for the first part, I'll just talk about ground states. Of course, I really want to talk about dynamics and representations of the Poincare group, but we'll get to that. But just ground states is already sort of interesting in that. So associated to every such Hamiltonian is a ground state, and we'll write that as omega A. Ground state, there it is. Now, at the moment, I've left the lattice parameter A to be kind of continuous. In fact, you can make your lattice discretization as general as you want. It doesn't even have to be regular. You could choose non-regular discretizations. It's totally fine. But it just adds complexity where there's none physically necessary. So actually, we're going to demand that our lattice spacings that we look at are in fact dyadic. Have it this way. So we're going to have dyadic lattice spacings. And where n is 2 to the power of n. That way, you can talk about halving a lattice cell. It's kind of nice, right? Instead of having to take 5 lattice cells and put it into 7, we'll just halve them. So it doesn't make any difference to the maths. And plus 1. Okay, so terminologically, that just allows us to write, and I will write, omega n for the ground state at lattice spacing an and h n for the Hamiltonian at lattice spacing an. And so I'm going to argue now, and I foreshadowed it all the way at the beginning with the classical situation, what do we really need to define a continuum? And so I thought long and hard about this for years, and then, wrote down a list of datum that you would need, what would you want, blah, 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 blah. And eventually, through endless discussions with my postdoc Cedric Benny and Alex Stockmeister, we sort of distilled out what I think is the minimum physical data that you need to compare a discretium with a continuum. And I already said it, right? You need to compare things at different scales. The goal of this talk is to extract and distill. Yep.
Well, but then, what do you even mean by the continuum, right? That is not a tautology. That you must see this as a certain limit that's kind of implicitly.
Yeah, I think you're seeing 10 steps ahead here. Yes, indeed. So what I'm going to do is talk about comparing things at different scales. And then once you've got that, it turns out you already have a limit. You can define the continuum as a quotient, the set of all quotient sequences. So, okay, that was the rest of the talk. Sorry, you can go. So, so the minimum physical data that we need is we need to be able to compare the system at different scales. What's the state of the system at some large scale? What's the state at some fine scale? Are they close, far? How do we do that? We need something extra, and that something extra comes from physics. It doesn't come from maths, it comes from physics. And this is something really crucial. There's 2 points where physics comes in, and no amount of abstract argumentation will avoid the fact that at the end of the day, we have to make a decision, and that decision will be based on physics. So the minimum key physical data will be a way to compare. So we've got the system at different scales. And you could say, well, how close is the ground state on the fine lattice here? How close is this state to say the lattice way down here, like omega 2? How close are these two ground states? We can't answer that, right? Because this thing lives in a Hilbert space with a different dimension to that Hilbert space there. No, we can't answer it unless we add in this key physical data, which is a way of comparing states at different scales. So we need a way to compare states at different scales. And the way we do that is we have to make a choice, no avoiding it. And the choice will be that of a map that takes states on finer lattices to coarser lattices. I mean, physicists have known this since the days of Kadanoff. It's absolutely nothing revolutionary. And what's the minimum requirements for such a coarse grading map? Well, it's got to take physical states to physical states, right? Otherwise, like, it's a kind of stupid map in quantum mechanical terms. So let's say we need a CP map. It should be at least a CP map. And this CP map takes states at some given fine scale and coarse grains them down to some state at some given coarser scale. It states at whatever scale n2 to states, coarser states at some scale n1. And it's a choice. Right? There's no magic here. We can't hope for the one true coarse grading map. You need to use physics to actually come up with a meaningful map. Yep.
Couldn't you just trace out the sites you added in when you went to Boston Labs?
That you can do. That's a perfectly legitimate map. Now you have to justify why that was the right map.
So that's, I would say, quite close to the statement of your correlation functions on the original sites.
Yep.
Right?
Yeah, it turns out that that map works. It'll give you a limit, but it's highly discontinuous.
Discontinuous, yes.
So now it turns out what is a good map? A good map is one that gives a limit where the dynamics act continuously versus discontinuous. That's I won't get to that today, but I can at least foreshadow that as well. So there you go. So a way of comparing systems at different scales. How do we do it? Well, you take your favorite state, and now this family of coarse graining maps that you've introduced based on perhaps some intuition about correlation. And then you can coarse grain a state. You can say, how close is this ground state to that ground state on the finer lattice? Well, I don't know, but what I could do is coarse grain this one down to this scale and then compare them. Now they're in the same space. Apply say, trace norm or something to ask how close it is.
So there's no need that the coarse grading map maps pure states.
There is no need for it to map pure states to pure states. That's really important, and very interestingly, as a consequence of the GNS representations, you can sometimes have CP maps that take pure states to mixed states, and in the end, the limit is still pure. All right, I think I've got about all the data I want to be able to explain this map over here. So here's the continuum limit. What do we need to talk about continuum limits, or comparing things with discrete and continuous, or comparing things at just different scales, which I would argue is already the hard data that we needed to work out. We need some data, right? We need some observables at the scale n. It's just like, how on earth do we measure things? For this audience, like observables just mean the matrices acting on the Hilbert space. But more subtly, if you want to go to infinite systems, we should talk about a quasi-local algebra here or something like that. The AN are the observables at every scale, n we care about. We need to have a Hilbert space at every scale we care about. That's given by wherever I wrote it. And we need, of course, Hamiltonians for every scale that we care about. And what else do we need for the continuum limit? We need these coarse grading maps. We need to come up with a physical argument why partial tracing is the right one, or flipping a coin and partial tracing the left cell or the right cell is a better map, or using wavelets as a way to coarse grade out in the single particle hoop. There's multiple ways you can introduce RG. I mean, for every Kadanoff RG, there's a corresponding map. So you need those things, but you also need these coarse grading maps for all n2 greater than n1. And it's worth pointing out that we probably want that these set of coarse grading maps has some additional properties. It's kind of stupid if they don't fulfill this property. You want that if you coarse grain the system not into itself, you get the same thing. Right? Makes sense, I hope. And you'd also want that if you coarse grain down N2, and then you coarse grain down to N3, that's the same as going from N1 to N3 in one go. Coarse grading ought to be just the same as doing the coarse grading from N1 to N3. And for the mathematically minded in the audience, what I've already written down here is an inductive system. So there's going to be a limit, an inductive limit, coming out of this, and that's how we define our continuum limit. And now with this data at hand, I can draw a picture, and that will explain this picture here. So here's a lattice system, some fine scale. And here's the coarse-grained version of it, and so on. And attached to each scale, there is a ground state, which I'll write as omega naught now. It's a mix, it's a density operator. And there is a coarser one in -1. And so on. And also, we have these CP maps here, right? We can take the ground state that we worked out by diagonalizing a horrible Hamiltonian, and we can coarse grain it once, and that'll give us another state. We might call that state omega 1. So here, these ground states here, these are initial scale ground states. They play a special role in that diagram over there. Circle them, here's what they feature. So these green things, what are they? That's what you get when you take your Hamiltonian at scale n and you diagonalize it, which is hard, right? Now note the word hard. So there's the hardness is here. It's literally in diagonalizing H. So if you take your Hamiltonian and diagonalize it, you'll get the ground state, no worries, if you have infinite computational power. And the rest of this diagram then, I hope, makes sense and is easier, right? Because the hard work that you did was in getting this initial diagonal sequence of ground states here. You need to really know the ground state at every scale. But once you've got that, then you're going to produce a whole network, a whole triangle, and this is Wilson's triangle of RG. And you can see exactly this diagram, but in the path integral formulation in his original paper. You can just apply your coarse graining map to take the original nice ground state of the system at scale m+2, and you can produce a coarse grained version of it now, a mixed state probably. It doesn't have to be pure. And then you can do your coarse graining map twice, and you can produce the twice coarse grained version of the system at scale m+2. And that produces or hands you a list of states on the same scale. And this is this is why this is important. We get a list of states on the same scale, but they're the descendants of ground states on much finer scales. And the hard work now is sort of, let me give a Bayesian prior for how hard you're going to work. You're probably going to work 99% hard in diagonalizing H, and 1% hard in arguing that this sequence of states tends to something, that this limit is well defined. So this is based on the work we've invested in studying well-known examples. So there is the sequence of states. You can compare each state horizontally with whatever fidelity norm you like, and you can ask, do these states tend to something or do they not tend to something? Maybe the limit is badly behaved. Maybe it doesn't even have a limit. Well, then you've done something wrong, right? You've chosen the wrong sequence of Hamiltonians. Okay, let's change our Hamiltonians, repeat. So that's where the hard work is. The hard work is in diagonalizing and then arguing that this sequence of states has a limit. Once you've done that hard work, the rest is easy. So in the last remaining minutes, I will give you a definition of the continuum limit, and then just probably stop there.
still have quite a bit of time.
I understood I had
20 so it's like 20 more minutes.
I started at 11. Oh, I have more time.
Yeah.
Oh, well, I won't torture you for too much longer. I mean, everyone is probably happy to go to lunch at some point. I mean, I don't really want to go past like 12:30. That would be bad. Yeah.
12:25.
12:35, right. Yep.
So, like you say, the arrows to the right, this is like the easy part.
Yep.
But I was under the impression that it was so quite hard for people to say like, well, we have something that looks very renormalizable, but whether up to all orders of perturbation theory, it really does. Like whether there's like a lambda pole is very often not at all easy to prove.
That's not, yeah, but I would argue that the hardness of proving that is probably in that you don't have a very good representation for these things to start with.
So, I mean, what do you mean proving? So if you have any finite set of these ground states,
Yep.
then you do need some proving to do, which I imagine is very hard.
So based on the experience of the laws where we pushed this whole program through to the end. So getting you have your original unrenormalized sort of Bayer Hamiltonian, and you work out the corresponding ground state for every scale. That's generally speaking pretty hard, right? But then you've also defined your RG maps through whatever physical intuition you have. And computing the image of one of these hard-to-get states under one of these maps is easy, right? If you've done a good job of defining your RG.
Sure, that's easy.
So getting from comparing these two states is pretty easy. Also going 2 steps is not any harder. So comparing this with that is also not too hard.
Right.
So what we found, yeah, I can only give you an experience-based.
No, I mean, all of this is easy, but it's the existence proving that is.
Yeah, I mean, okay, yeah. I would say it's how you choose your Bayer Hamiltonians so that these limits are then well-defined limits. Hard. Yep.
If finding the ground state is so hard, why don't you just do Hamiltonian RG? Just put on the Hamiltonians and don't find the ground state.
I'm not sure what Hamiltonian RG.
If you directly renormalize the Hamiltonians, you could make some formalism where you're
Because we want to build a Hilbert space at the end. And okay, this is all fine and good, but the Hilbert space requires observables plus a state, a reference state.
So it doesn't answer the question you want to answer. Just
In the end, we want a Hilbert space, right? And so we want a state also in addition to all these Hamiltonians. And that together is what the interplay between state and observables is this GNS representation.
Yeah, right.
And that's where things start to get.
So that's because you're going to build your Hilbert space from a state.
Okay. Yeah, right. So that's where I was in the Wilson triangle. Okay, let's now write some definitions because we've got the triangle. Okay. So the first thing I want to introduce is the scaling limit state at scale n. What's that? Well, I wrote it down already on Wilson's triangle over there. It's when you take the horizontal limit. So that implies, of course, that that limit even exists. Then there's sort of a nice corollary you can get of this definition. The scaling, and I claim that you'll invest all your energy in getting that to work out. Based on the experience we have of all the examples we've studied so far, or list of the examples we've done so far, you'll find that you're investing a tremendous amount of energy proving that that limit exists and what it is, right?
It's important that it's really converging
Yes.
with a unique limit.
Yes. Okay, if it does, I don't know what happens if it say has 2 points of accumulation. Maybe you get something interesting out of it as well. But
That you always have.
yeah. So okay, there's a corollary. Once you've done that though, there's something really nice, and that is that this state is completely invariant under coarse graining. Kind of trivial, but still, I think that's really nice. And in fact, that makes the second definition trivial as well. So all the hard work's been done. So the actual continuum limit is the double limit now. It's the one where you also take n to infinity. But the existence of that is straightforward if you combine these 2 things.
And the limit doesn't, the order doesn't matter.
Oh, well, the order does matter. Yeah. You have to do it this way, then that way. Actually, I don't know. Maybe you can use some examples. I don't know the answer. Yeah. All right. So that's the scaling, the continuum limit. And in a way, that's the take-home message now of the talk. But this is only interesting once I explain to you how examples fit into this. Now, Landau poles and so on, it's a very deep question when you ask, because what you're saying is, okay, I have QED, and I regulate QED, so I've got myself this list of Hamiltonians of regulated QED. I solve QED, right? I don't know how to do that non-perturbatively, but let's suppose I could. And then, I have this list of ground states. And then there is a kind of clear RG map for most scalar field theories and vector fields. You just it's literally flip a coin, trace out left or right. And then I RG these ground states. It's a bunch of boson systems. And then I take the limit. So I'm scared of even contemplating that particular example. But and then I check if the limit exists, and the Landau pole will presumably, and I don't know the answer because I can't work this out, manifest itself in the non-existence of these limits there.
It should look like it exists for a while.
Right.
The problem with it is that it deceives you.
Yeah, you think it's fine, and then, oh crap. Yeah,
Something like that.
Yeah, I don't know, and it's just based on physical intuition. I can't really give you like an answer. Because I just don't think I have the tools to answer your question yet. I mean, maybe, taking the lattice QED Hamiltonian and diagonalizing it. Let's say we accept the perturbative perturbative answer. It's probably a really interesting research project. I literally have no intuition how that'll play out, but apart from what we already discussed. But what I do want to do is talk about cases where we do know what to do. Okay, you'll be disappointed, but okay, prepare yourself for disappointment. Yeah.
Does this definition of the double infinite, does this imply that it's, I mean, your coarse graining map is essentially one CP map to coarse grain one scale, and then you just repeat the same CP map? Does this imply that the double limit is the fixed point of that CP map?
Basically,
yeah. So, but that basically means that the outcome is completely encoded in the CP map.
No. Because we're also, it's not quite the fixed point, because the pre-image of the map, if we let the CP map just go forever, sure, we'll land on the fixed point. Boring. It's always boring, right? It should be boring for a good RG. But what we're doing is subtle. We're actually taking the pre-image of this map to be ever further away from the fixed point. So that, you take some pre-image, it's really far from the fixed point, you apply the map lots of times, you end up on something. Okay, let's take it even further away, but apply the map even more times, and we land up on something, and that's what these things are, right? So there's this, we actually don't go to the fixed point of this coarse grain. That's what fine-tuning is here. Yep.
You give us the RG, you define the RG transformation, then in principle that tells you how to construct renormalize your rotor. But do I understand correctly? Here you have E, or whatever, E, which is a map on the states.
Yeah.
But you still have to somehow find some other way of saying what the H's should be.
Yes. I mean, in a field theory context, this is more or less God-given. We just take the Wilsonian, like, integrate out shells. And then, I'm trying to translate this to a...
I just mean, when you've chosen what your E should be,
Yep.
in principle, how do you work out the sequence of H's?
By doing physics. By, having a continuum theory in mind, usually, and then building the cutoff in the most naive way possible. That's by whatever lattice cutoff.
So then this sequence of identities becomes somehow approximate when you're really
So just one more question.
Yeah.
You understand it correctly, your omega sub-infinity dependent on n, it's just a state on n qubits.
Yes. Right. Two. How did I do it?
2 to the n.
2 to the n
Two
qubit.
to the n qubit.
Lots of qubits.
Right. And then you take the limit n tending to infinity. Which, if you think of as a state on an infinite chain,
You should, yeah. So now we have to...
have some weird structure.
Hopefully some weird structure, yeah. I'll do an
Not
example.
translation variant. No.
It will be translation invariant.
It will be translation.
Yeah, because as long as we ensure that these things are translation invariant and these CP maps that take translation invariant states are translation invariant states, then we're good. And often the CP maps might not be translation invariant, but still you end up with translation invariant. So I'll write down a couple of quick examples in the remaining minutes, and just give you a sense of like what do these things even look like, right? What am I talking about? Right, let's take a very boring model. Because even this very boring model gives you quite a lot of intuition about all these things. So this is obviously the trivial fixed point. It's just a magnetic field. And we're going to define the following RG map. I'm going to define it in terms of observables. So I don't know if you can shredding a picture up to now, but I'll just do it in the shredding picture. So if I put in a state, then this map flips a coin and traces out the left cell or the right cell. That's what gamma does. So with probability of half, I trace out the right cell, plus a half, trace out the left cell. And you'll see what I mean in a second. And the actual RG map will be gamma, tensor gamma, tensor gamma. So you can see that takes two neighboring lattice sites, the state of neighboring lattice sites with 50% probability, traces out that one or that one. And in parallel does it to the next pair and so on like that. So then, okay, we know what the ground state is of this thing for all scales. It's just a tensor product of the zero state here. Nice simple product state. And actually, well, it's a fixed point already of this RG. Whatever, n1, let's say. And actually, if we go to Wilson's triangle, we can see what we've got now. We've got the product state everywhere. We've got the product state here. We've got the product state down here. And so, well, yeah, great, right? Just got a product state. Okay, so you should not be impressed by this. But at least it sort of tells you, okay, this thing hasn't created something that isn't well defined or doesn't exist. What other examples? Well, you can do the Klein-Gordon field. If you take the Klein-Gordon field, discretize it on a lattice, you get a bosonic harmonic chain, and then you have to be a bit more careful. You have to use you have to introduce a RG map. We found wavelets to give a really decent RG map, but actually momentum shell RG just works really, really well. you go to Fourier space and just trace out the high frequency mode. That works particularly well. So that works, and it gives you something at the end, and that something has all the properties that the Klein-Gordon field does in the continuum limit, so tick. In particular, it gives you a continuous representation of the Poincare group, so, right? But it better have done if it was a good continuum limit. The Dirac field works as well.
So for the Klein-Gordon example, what are the first limiting states?
What do they look like? Yeah. In momentum shell RG, they just literally take the state and define a system, trace out the high frequency modes until you're down to momenta up to M, or up to N, sorry.
I mean, it remains pure state then?
No, it's not pure. But the limiting state and the representation you get is pure.
How does it get mixed? Because it's a state in moment. I mean, this.
The initial state. Actually, maybe we do a Bogoliubov first. Maybe we cheat. Maybe it is actually a pure state. I can't remember the details of that one. The Dirac field in 1+1 we've done. 2+1 not yet, but I have no doubts it'll work. In 1+1, I mean, although we have fermion doubling to worry about, which okay, I won't talk about fermion doubling.
Do you have any kind of a thing where if you have different size, that you are guaranteed to, if you find something, that you find the same thing for the universality language?
No, not yet. Although it should be. It should be. So the Dirac field you can get by diagonalizing some funky spin system that you can work out. And actually most recently, and the one that we are happiest about, is the transverse easing model. We've worked out the continuum limit of that, and it's the easing CFT, as you might hope. But that's super non-trivial, because you've got non-local symmetries in this model. So that one's going to come out in some paper soon. So, but hopefully this works for a lot more than just these small list of examples. Oh yeah, the KG field, by the way, works in D+1 dimensions, right? It's definitely not restricted to 1 dimensions. What else can I say? Yeah, anion chains, we hope that this will give us rational conformal field theories at the end. That's the stuff dreams are made of at the moment, so we're not quite there yet.
Speaking of dreams, I fall like interacting people.
So Alex informs me that in 1+1 dimensions, this will work and we'll get 5. But why? Because we just open Glimmer and Jaffa and copy out the required information. So the hard work's been done back in the constructive quantum field theory days, and so by leveraging that work, you do get. Apparently, I haven't looked at the details of that. The continuum limit will work out for this 1+1 dimensional case, and I think probably any constructive quantum field theory, for example, would probably be pushed into this framework.
So you just take the transfer field always, like every Hn is always just transfer field U.
No, we have to tune the coupling constants at scale.
So you're not at the critical point, or what do you mean?
Wait on. No, yeah, always.
Always just the same. Yeah. So in a way, this really does gives you just regular RT.
Yeah.
Oh. How good do you get your exponents out of it?
The critical exponents.
Yes.
Exactly. So we get the. Yeah, but it's in the continuum limit. So the dimensions of the operators are. We get the primary fields and from.
So you can take any critical model where maybe you don't know.
hang on. We talked about the transverse easing now. Any critical model, yeah. No,
I mean, it sounds like you have a prescription to just plug in any critical model, and you find the RG QFT, and then you have an exact description of this.
Okay, in a way, this is an excellent question, and highlights what's hard about this. So let's go back to the minimal data that you need. We need the Hamiltonian, but we also need the RG map. And the problem is the RG map that we use for the transverse easing model uses the fact that we know there's a fermion representation. So we use wavelets on fermions. if you give me another critical model, POTS or 6J or whatever, your favorite critical model, I now no longer know what's a good RG for that model. And this flipping the coin thing doesn't work. It gives bad limits. And I can't give a good answer why yet. So yeah, don't get too excited.
I was warned.
Yeah, prepare for disappointment. Good. Anyway, on that bright and happy note, I'm going to go now. So thank you very much.